Welcome back. So we will take our final example, that of the classical ideal gas, and treat it canonically. So our system is n particles in a box of volume V in d dimensions. So the Hamiltonian of this system is sum over I equal to 1 to n pi raised to the power nu, where there's a k outside or kappa outside, where pi is mod pi, right? Such that h is a homogeneous function in P with degree nu, right? So given this Hamiltonian, two cases are of particular interest for us. One is nu is equal to 2 and k is equal to 1 over twice m. In that case, the Hamiltonian becomes pi square over twice m, which is a non-relativistic ideal gas. The second case of interest is nu is equal to 1 and k is equal to c, in which case this is sum over pi times c, and this is an ultra-relativistic gas. We'll come back to these special cases later on, right? So given this Hamiltonian, we write down the single particle partition function as d dq d dp. Since it's a d-dimensional, e to the power minus beta k pi raised to the power nu. Now you notice that this quantity is still dimension full, therefore because it has a dimension of q times p, which is the dimension of action, and therefore you divide this one by 2 pi h bar raised to the power d, right? This exponential integral, this part, does not depend on the coordinates, and therefore we can straightforward write down this as 2 pi h bar raised to the power d integral of d dp e to the power minus beta k pi. We will not put the index I over here anymore because it's just a single particle now, p to the power mu, which is v over 2 pi h bar raised to the power d dp p to the power d minus 1 e to the power minus beta kappa p to the power mu. But this is not all of it, because we still have to take care of the factor a3n that we did for, right? And that answer is d by 2 gamma d by 2. So this quantity is v over 2 pi h bar raised to the power d. So this is the part which comes from the angular integral 2 pi d by 2 gamma d by 2. And then I have the integral dp p to the power d minus 1 e to the power minus beta kappa p to the power mu. Good. Once I have this, then I now want to evaluate this integral, but for that let me substitute y as beta k p to the power mu, right? So that dy is beta k nu p to the power nu minus 1 dp, which is equal to nu times y dp over p. So that dp, the change of variable, gives me p nu y dy, and this integral, if I calculate now, this becomes dy p nu y, I have p to the power d minus 1, which is p to the power d by p, so that this p and this p is going to cancel out. That's why I wrote this differential in terms of p, and I have e to the power minus 1. So this gets cancelled out. I think there is something wrong over here, so I can see that this is going to be dp is going to be p over nu y. So I will have p over nu times y, and this p cancels out, so you will be left off with dy 1 over nu 1 over y, and from this p is y over beta k raised to the power 1 over nu, so y over d by nu beta k d by nu e to the power minus 1 so e to the power minus y. So your single particle partition function is v over 2 pi h bar d. Do not be afraid, because with this all RP symbolic integration like k, d and all this, I'm sure you would have done it somewhere. And 1 over nu 1 over beta k raised to the power d over nu dy e to the power minus y y to the power d by nu minus 1. This integral is a gamma function, gamma d over nu. So now you see that I have solved the problem. I have 1 by nu gamma of d by nu beta kappa d over nu. There is one mistake. I think I have forgotten a gamma d by 2 factor. 1 over gamma d by 2. 1 over gamma d by 2. Right? Let me write this as v over lambda t, where lambda t, you see, has the dimension of volume. So lambda t I can write down in terms of lambda cube t, and this quantity lambda t is called the de Broglie wavelength. Right? Okay. So q then becomes v over lambda t, and then lambda t is beta to the power d over nu divided by a constant cd nu. And this cd nu, if you just put it over here, you can immediately read off what this is going to be. This is going to be 1 over 2 pi h bar d gamma d by 2 nu gamma d over nu, and then there is going to be kappa d over nu. So let's see whether we have the right expression and everything. So this is the term which is the angular integral, and I think we have missed out 2 pi raised to the power d by 2. So 2 pi raised to the power d by 2 over here, so that there is a 2 pi raised to the power d by 2 sitting over here. So this is the expression for given any arbitrary dimension d and a value nu. One can construct the de Broglie wavelength from here. We'll come back to this. We'll explicitly derive this expression, particularly for the case of k equal to 1 over 2m and nu is equal to 2. But right now let us continue with this calculation. The n particle partition function is q to the power n. And now we bring in the factor n factorial, because the particles of this gas are indistinguishable. You cannot distinguish one from the other, and therefore you are overcounting your microstates. So the total possible permutations, total possibility of overcounting permutations is n factorial, with which you divide this, which implies the free energy, which is minus kBt ln of Zn, is going to be minus kBt n, we'll put that in a bracket, ln q minus n ln n plus n, and this becomes minus n kBt ln v over lambda t 1 by n plus 1, right? So this is your free energy. Therefore the energy E is kB t square del t of ln of Zn. And if I look at ln of Zn, ln of Zn is ln of v over qt, v over lambda t n, which is kBt square del t of ln v over lambda t, which is kBt square del t of ln of v minus ln of lambda t, and therefore you have kBt square minus del t of ln of lambda t, right? Good. Lambda t by our definition was beta to the power d over nu divided by c of d comma nu. So del t of lambda t is del beta of lambda t into del beta del t. Del beta del t is minus 1 over kb t square del lambda t del beta. So I just have to evaluate this, but let's take a log of this expression. Ln lambda t is d over nu ln beta minus ln c d comma nu, the constant over here. So del lambda del t beta, let's say, so 1 by lambda t, if I now take a derivative with respect to beta, then d over nu 1 over beta. Am I right? Yeah. So del lambda del t del beta is equal to d over nu lambda t over beta, and therefore I have minus 1 over kb t square times d over nu, sorry, this is d over nu lambda t over beta. We'll keep it like this way. So this becomes your del lambda t del t, right? Let's go back to the energy expression which we had over here, and the final form was this, is minus kb t square del t of ln lambda t is 1 by lambda t del lambda t del t. Actually, we could have avoided all this exercise, just taken a derivative of t with respect to just this one, then life would have been simpler. Anyway, since we have done it, let's just go ahead with this kbt square over lambda t. Del lambda del t I know is minus 1 over kb t square d over nu lambda t over beta. So this means this cancels out, this cancels out, and I have the nice expression d over nu kbt. Right? Therefore, for a non-relativistic gas, when nu is equal to 2 in 3 dimension, d is equal to 3, you see E is equal to d over nu. I'm sorry, there has to be an n which I have missed somewhere. D over nu kBt. But you see, there is a problem over here, and the problem rests in this part. Now, when I wrote down this had ln Zn is n ln V over lambda t, and I missed out a factor n over here. So that n factor has to be carried all throughout, and once you do that calculation, you're going to come up with an n over here. If you did not have an n, that means the energy was not extensive. So there is something wrong, seriously wrong with the calculation. So one has to be very, very mindful of all of these, right? So if nu is equal to 2 and d is equal to 3, I have E is equal to 3 by 2 nkBt. And this is the classical ideal gas that we have seen. When nu is equal to 1 and d is equal to 3, E is equal to just nkBt. Strikingly different than 3n kBt. It is strikingly different from the result that we have seen for this case. Now recall that F was U minus Ts, and unlike the magnetic system that we had seen, this is not the Gibbs free energy. There is no external pressure imposed. So therefore dF is du minus Tds, and one can work this out. This is going to be minus dPdV minus SDT, so that del F del V is going to be minus of del F del V is going to be the thermodynamic pressure. Let's look at the expression for F. F had this very nice expression minus nkBt ln V over lambda t n lambda t plus 1, which means I can just explicitly write it down as ln V minus ln n minus ln lambda t plus 1. And if I take a derivative of the free energy with respect to the volume, these three terms will not matter. Temperature held constant is minus nkBt over V. So that minus of del F del V temperature constant is just plus this, and therefore this is the pressure. So you have PV is equal to nkBt. Remarkably, it does not depend on whether it's an ultra-relativistic gas or whether it's a non-relativistic gas. So it does not depend on nu, it does not depend on K, it does not depend on D. It is just that the pressure times volume is equal to nkBt. Where does the difference come in? For a non-relativistic gas, this is going to be 3 by 2 nkBt, whereas for a relativistic gas, the energy relation is different, right? So nkBt is PV. So I will just replace this 3 by 2 PV for a non-relativistic gas, and for an ultra-relativistic gas, this is equal to 3 PV. Immediately you see that the pressure is 2/3 the energy density, which we'll write as small e for a non-relativistic gas. For a relativistic gas, the pressure is 1/3 the energy density. So this is the case for a photon gas, and this is the case for a normal ideal non-relativistic ideal gas. For a non-relativistic ideal gas, the pressure is always 2/3 the energy density. Your small e is capital E over V, and for a ultra-relativistic gas, such as a photon gas, your pressure is always 1/3 of the energy density. So what we now want to discuss is what is called the equipartition theorem. It's a very useful theorem, as you will see in the following discussion. So let's denote the phase space variable. So let the phase space variables be xi, and these include my coordinate and momenta. So for a system with n degrees of freedom, for a system with n particles, there are 2n degrees of freedom in 1D, right? So if it's in 3 dimension, then it's a 6n. Anyway, that is not the concern over here. So xi, the set qi pi, is denoted by the xi, right? So now I want to determine the average of this quantity del h del xj, where h is the Hamiltonian. Right? So by definition, xi del h del xj is equal to 1 over z d of xn, which means x1, x2, all this thing, e to the power minus beta h xi del h del xj, right? Now let's just focus from this expression in the right hand side, let's just focus on the integral over xj. So from this I just extract the term which is minus beta hj xi del h del xj, which I manipulate, or rather first rearrange, as xi e to the power minus beta h del h del xj. This is going to be d of xj xi del xj of e to the power minus beta h. If you do that, you are going to get a minus beta h, so I have to divide by minus 1 over beta. So this becomes minus 1 over beta dxj xi del xj e to the power minus beta h. If I now integrate by parts, then essentially I have 1 over beta xi e to the power minus beta h, the boundary terms, minus d of xj e to the power minus beta h del xi del xj. So just this part of the integral has now come to this. But these are the boundary terms. The first term vanishes because it's a boundary term, and therefore you are left out with 1 over beta integral dxj e to the power minus beta h del xi del xj, which means this average xi del h del xj is 1 over z dxn minus beta h del xi del xj, and a 1 over beta outside. Therefore this expression becomes 1 over beta. The del xi del xj is delta ij, so we'll put a delta ij, and then the rest of the expression is nothing but the partition function. So this becomes kbt times delta ij, right? So this would imply that xi del xi average is kbt. xi del h del xj is 0 if I is not equal to j. Now suppose the Hamiltonian depends on f such values. Suppose the Hamiltonian depends on f values of xi, that is x1, x2 all the way up to xf, right? Then it means that sum over I equal to 1 to f xi del h del xi is equal to f times kBt. This particular expression follows from the one that we have written down over here. Good. Further, we take it now one more step. We assume that h is a homogeneous function of degree nu, right? So normally for the ideal gas we also had this to be a homogeneous function. We just did it for this a little while ago or in the earlier class. So h is a homogeneous function of degree u. Then I can apply my Euler theorem to write down this as nu times h, right? Sorry, not this. And this theorem we have done earlier. Once we substitute this over here, this essentially means that nu times h is f over times kBt, so that the average of the Hamiltonian, which is equivalent to the average energy, is going to be f over nu kBt. And this is the generalized equipartition theorem, right? For a non-relativistic gas, I have pi squared over twice m, right? Now, so I runs from 1 to 3n. Therefore, your f is equal to 3n, which means sum over pi del h del pi average I is equal to 1 to 3n is going to be 3n kBt. But del h del pi is just pi over m. So therefore, this is sum over I equal to 1 to n, and you can easily see that pi times del h del pi is py square over m. We can multiply it by 2, divide it by 2, take the sum over here, take the sum over here, is just 2 times h. So it's a homogeneous function of degree 2. But nevertheless, this would mean that the average energy in this case is going to be 3 by 2 nkBt. More explicitly, if this is pi over m, average is 3n kBt, or average pi square over 2n, sum over I equal to 1 to 3n is going to be 3/2 nkBt. So the total kinetic energy of the system, which in this case is also the total energy of the system, is 3/2 nkBt, and this immediately follows from the equipartition theorem. If I had h as sum over I c pi, then you see your average energy your nu is equal to 1. It's a homogeneous function of degree 1. It's going to be 3n kBt. The result that we derived so laboriously a little earlier, right? For n harmonic oscillators, in 3 dimension, your degree of freedom, your f is 6n. It depends. Your Hamiltonian is sum over half m omega square xi square plus pi square over twice m, where I runs from 1 to 3n, I also runs from 1 to 3m, so you have 6n degrees of freedom, and nu is 2. This Hamiltonian is a homogeneous function of degree 2, so that the average energy in this case is f over nu n kBt, f over nu kBt, which is going to be 3n kBt. And this is exactly the result we derived when we treated such a system in macrocanonical ensemble, right? Our last point to note in this particular discussion is, let's say I have del h del xi is kBt. So if I choose xi is equal to pi, which will imply that pi del h del pi average is equal to kBt. But del h del pi, if you recall your Hamiltonian equation of motion, del h del pi is qi dot. So pi qi dot is equal to kBt, right? Similarly, if you choose your xi as qi, then this is qi del h del qi, which is going to be kBt by the equipartition theorem, and del h del qi is minus, so pi dot is minus del h del qi, and therefore you have del h pi dot as minus kBt, right? So now if you sum it over I equal to 1 to 3n, then essentially this becomes I equal to 1 to 3n, so that sum over I is equal to 1 to 3n, qi pi dot is equal to minus 3n kBt. Now this particular expression has very significant significance in statistical mechanics. If you look at the dimension of this is r dot f, and therefore this is a work done. In statistical mechanics, this is called the virial, and the work done in a hydrostatic system particularly is related to the pressure. So if you want to calculate the equilibrium pressure, one has to evaluate this virial together with the kinetic energy or kinetic contribution. One gets the thermodynamic pressure from the microscopic quantities.